Now we consider a thin plate, so this is the thickness of the plate, whereas A is the width of the plate along the x direction, and B is the width of the plate along the y direction. So we have a rectangular plate, if we see it from above. And we have also some loads, and these loads can be represented as a function, let's say q of x and y. You can see that, this function depends on these two coordinates. So depending on where we are on the plate, the intensity of the load might differ because this is a function. So it might also be a constant, but we want to be more general, so this is a function. And these loads here are perpendicular to the plate, so they are along the z direction. Z is the normal to the plate. From the classical theory of plates, we know that the operator, the nabla operator to the fourth power, which is equal to the Laplacian squared, applied to W is the displacement along Z of a generic point of the plate, so W of x and y, it is a function of x and y. This is equal to the load, Q of x and y, divided by the constant d. D is also known as the flexural rigidity, and it is a function of other parameters of the theory of elasticity that I don't want to get into now. This is just a constant which is known. And now we want to represent the generic load q of x and y in terms of a Fourier series, in particular in terms of a double Fourier series. So this is the way in which I will represent the load q. There is a first summation over m from 1 to infinity, a second summation over n from 1 to infinity. We have amn, which is the generic coefficient of the Fourier representation. This is a bidimensional Fourier representation. Then we have two functions of x and y. So we have one function of x and the other one is a function of y. In particular, these functions are sinusoids. So we have the sine of m pi x over a and the sine of n pi y over b, like this. So you can see that, this is a Fourier representation of a generic load, but we can see that, for example, when x is equal to 0 or x equal to a, this sign will go to 0. So it means that q will be 0 at the boundary. So q of 0y equal to q of ay equal to 0. And similarly, you can see that when y is equal to 0 or y is equal to b, also this sign would be 0. So q of x0 is equal to q of xb, which is equal to 0. So this is an assumption. And apart from that, this load here is very general. We can construct basically any kind of function which complies with these constraints. We also need to be able to reconstruct, to calculate these coefficients a, m, n. We can assume them to be given, but for example, for a generic function q of x and y, which we want to expand in this series, we must be able to calculate these coefficients. And the formula for that, amn, the formula for amn is the following: 4 divided by ab, integral from 0 to b, integral from 0 to a, then we have q of xy, sine of m pi x over a, sine of n pi y over b, dx dy. So with this formula and this formula, we are able to basically reconstruct a generic function q of x and y, which complies with this constraint. But in this case, we are using a Fourier series, so in a double Fourier series to represent the function. This is particularly convenient because once we represent the function like this, it is straightforward to calculate, to solve this differential equation, which is not so trivial otherwise. And in particular, we can do that by assuming, and we will show that indeed we will find the solution. We can assume that w of x and y is a similar function, so we can expand it in a Fourier series, and the expansion is very similar to the one that we used for q, sum over m from 1 to infinity, sum over n from 1 to infinity, wmn, so we have different coefficients, but the functions that we use to expand w of x and y are the same. So we have the sine of m pi x over a and the sine of n pi y over b, like this. Now at this point we need to calculate nabla to the fourth of w. So nabla to the fourth is equal to d squared dx squared plus d squared dy squared squared. And this can also be expanded like this, d4 dx4 plus 2 d4 dx squared dy squared plus d4 dy4. So we need to calculate this derivative, and this derivative. Now, it is quite straightforward to calculate d4w dx4 because, we have sinusoidal functions. So it's quite easy to see that we have the summation over m and over n. So I am representing these two summations with just one symbol for the sake of simplicity. And we have m pi over a to the 4 wmn sine of m pi x over a sine of n pi y over b. So you can see that the operator, this derivative operator, these four derivatives will only act on this sign to produce this coefficient here in front of this wmn. Similarly, we can calculate d4w dx squared dy squared, which is equal to summation over m over n. In this case, we are going to get m pi over a squared n pi over b squared wmn sine of m pi x over a sine of n pi y over b. And finally, we can also calculate d4w dy4, which is equal to summation over m over n. In this case, we are only going to act on this sign here. So we are going to get n pi over b to the 4, and similarly we get wmn sine of m pi x over a sine of n pi y over b. So from this, we can see quite easily that we get nabla to the 4 w equal to the summation over m over n. We have m pi over a to the 4. Then we get this multiplied by 2. Remember, because there is a coefficient of 2 here. If you want, I can put it here for the sake of convenience. So we get plus 2 times this. And then we also have to sum over this. We have to sum this. And you can see that instead of writing all of this, let me put these 2 back. So we can square this, and we can add n pi over b squared, and then we square this, and this is exactly equal to this plus this plus this. So it's another way of writing the same thing. And then we are left with a Wmn sine of m pi x over a sine of n pi y over b. And we can close this bracket. I mean, this square bracket here is not important, actually. This must be equal to q of xy divided by d. And q of x and y can be written as an expansion, a similar expansion, very similar to this one, but instead of this, q of xy contains amn. Since we have to divide by d, this quantity here that I have framed must be equal to amn divided by d. Simple as that. So at this point, we can say that Wmn must be equal to Amn divided by d, and then we can also factor out pi to the fourth. We have m squared over a squared plus n squared over b squared all squared, like this. From this, you can see basically that thin plates act as low-pass filters. Why is that? Well, because you can see that for high frequencies, when m and n are large, this denominator will grow, and you can see that there is also another square here, so it will grow quite fast, and therefore these coefficients here will become smaller as m and n grow. So only the low frequencies, quote-unquote frequencies, are important to characterize the behavior of the plate.